Hi, I'm Sala, and in this video we are going to simulate and animate the equations of motion of this carousel which we modeled in previous videos. Basically, we made an abstraction of the problem as a 2-degree of freedom mechanism in which I could input a torque on this rotation axis to move everything, and then via suitable kinetic and potential energy balances and Euler-Lagrange equations, we were able, with a little help from the Symbolic Toolbox in Matlab, to derive these equations of motion. And of course, what we must do is solve for the accelerations. More on that in a minute. As in fact, yes, solving for accelerations is the important thing. Usually in robotics textbooks, you get the equations of motion written like this, in which a mass matrix multiplies the acceleration vector. But okay, it's just a matter of how you interpret the equations of motion, which are what they are. This thing and this thing. So, how can we simulate it? Well, we will need to express things in a normalized state space equation as follows. This mechanical system with two mechanical degrees of freedom is a fourth order dynamic system, in the sense that we have two positions and two speeds as state variables, and we can write the time derivatives of these four things as a function of themselves plus the external torque. Indeed, the time derivative of phi is omega 0 by definition, because we named it that way when setting up the modeling equations, and the time derivative of zeta is omega 1, again by definition. Then the time derivative of the omegas, so angular accelerations, well, I need the Euler-Lagrange model in order to solve for them, but okay, as we did it before, then I tell the Symbolic Toolbox of Matlab to solve for the accelerations in the equations of motion. So the result of Matlab, alpha 0, will be the time derivative of omega 0, and alpha 1 will be the time derivative of omega 1. So these are the four state derivatives that constitute the state equation. But of course, as the left-hand side is always the same, state derivatives, we just need to store for our code the right-hand side of the equalities, which are the actual expressions of such state derivatives. So good. The only thing we need is to simulate this with, say, the Runge-Kutta ode45 integrator, but as this is a Symbolic Toolbox object, state equations fourth order, then we need to do a little bit of bookkeeping to transform that to ordinary numerical functions and expressions in order to carry out numerical simulation. So let's do it in a separate Matlab file as follows. We'll first insert into Matlab's workspace actual numerical values for the constant parameters in my model. And then with the command eval, this EEE will be a new Symbolic Toolbox object in which all the above constants will have been evaluated to their actual numerical values, so there will be less symbolical variables in EEE. Let's see. EEE is an expression in which only these four letters appear, which is correct in the sense that the allowed symbols in the state equations are the four states and the external input torque, and in this particular case it seems that one of the states, phi, does not influence the derivatives of this stuff, but okay, in an abstract sense, it might appear in the equations and still they would be correct. So we have only these 4 letters, or 5, including phi, to be formally correct. Then I will compile this EEE as a function of those letters. I will tell that MATLAB should output a numerical function so that 5 numbers enter these 4 states and 1 input, and 4 numbers exit the 4 state derivatives. This extd for num is the bloody name I put for that stuff. And then as input in a simulation is an arbitrary function of time, then I'll set my torque to this function of time. I just invented it. You can put here whatever function of time you wish. You can download the code and play. The thing is that once I have this external torque function of time, I can prepare everything for the numerical simulation, because numerical integration routines in MATLAB need the clock, lowercase t, and the state vector x. And then they must output the state derivatives. How? Well, evaluating this stuff I compiled from the Symbolic Toolbox by introducing into it the 4 state variables and the input. So this estado ode, well, I'll change the name to something more English sounding. This state equation for ODE is ready for simulation. So after all this bookkeeping, nothing conceptually important has been done. It's just nitty-gritty details of MATLAB programming. Then I set initial condition and I carry out the requested simulation. So this is sort of a cumbersome, error-prone stuff. We need to transform from these equations of motion in the Symbolic Toolbox language to what the numerical integration and simulation routines require. But okay, once we do it, this is it. We finished the simulation, so the only thing now is plotting the results. We have 2 ways. First one, well, states x is a function of time that I can plot with, say, this kind of code. I am plotting the second and third states as a function of time. I mean the theta angle of the hanging mass and the platform angular speed. But I mean, you can plot whatever state you wish, or the 4 of them. As I said, download the code and play. The thing is that, well, that plot, here we have it, is correct, but sort of difficult to understand. We can gather richer intuition on what we are doing if we see something like this moving. So we'll now pursue making an animation. But we'll first see the animation result, and then later on we'll delve into the code to generate it. Because, well, the important thing is understanding what we are simulating from a physical and engineering point of view, and then the details on how to plot the animation is kind of a lower priority issue you can skip at the end of the video if you wish so. So if I execute this code, then a window opens and we see the animation of the oscillations of my pendulum, in which my torque is increasing and increasing the rotation speed of the orange platform. And then later on I put a negative torque to break the platform, so the rotation speed diminishes and the angles also fall down to the vertical orientation or close to it. This is the simulation. Slowing down, about to end. So, if you are curious about how to encode this, then let's go to the code. And basically, with this MATLAB function, I create a numeric function that transforms angular positions of the phi and theta degrees of freedom into the 3 xyz positions of the hanging mass, this is what we do in this line. In here, I replace the variables phi and theta with the actual result from the simulation. So rsim is the hanging mass position at the simulation instance. And then this is the animation loop. Each k is one frame. So this line plots the blue trailing line we see here. Of course, that's optional, but somehow it makes a more beautiful figure, and it makes our eyes to better grasp the actual movement of the black dot, which is the actual hanging mass. Then this line, we are doing a plot 3, of course, in 3D space. Well, this thing plots the orange platform you see there. This plot 3 line plots the yellow bar between the platform and the suspended mass in here. And last, this line plots a big dot in black representing the hanging mass, as we have there. But as I said, all the conceptually important stuff is carried out in this couple of lines. The rest of lines in our code are just bookkeeping to transform from symbolic to numeric and to plot beautiful things. So we'll end here. In this video, we have shown how to manipulate the symbolic result from Euler-Lagrange equations of motion in order to solve for the accelerations, to build a fourth order normalized steady state representation, and then to simulate it with ode45, plotting the results as a function of time, or better, plotting them in this 3D animation to better grasp the intuition on the kind of movement we are simulating. So this is it. We end here. Thanks for your attention.